So what we would do is take those DIMMs and the higher the frequency DIMMs, typically they give you really great bandwidth, but they might be lacking a bit in latency. And we would tune those. Often we would reduce the frequency, but that would allow us to reduce the timings as well. And we'd end up with a kit that could read and write data, small amounts of data very quickly, and better than the stock DIMMs that we had bought.
Okay, good morning and welcome back to another episode of Making It Happen by Sims. So funnily enough, the last episode that I recorded with Exacta, and it was with the brilliant Nick Rogers in the exact seat that our guest is sat today. But I'm excited to say that we're back for another great chat today with another great mind from Exacta Group, specifically James Lupton, who is the CTO of Blackcore Technologies. James, how are you?
I'm good, thank you. Thanks for having me.
No worries. Thanks for joining us. I know you're a busy man, especially been stateside quite a bit, I want to imagine. So,
yeah, I think 3 times in the last couple of months. We're going back again in October for another event, so it's just
nice.
a lot more travel than I'm used to. But it's really nice to be able to see these places. I wouldn't get the chance to go to certainly like New York and go to the financial centers within New York. It's a great experience.
And is it solely New York that you guys are doing a lot of your work, or is it spread across east to west?
We do it kind of all over. There's different teams in different places. A lot of these firms, they'll have maybe a center within New York, but they'll have teams maybe in Chicago, things like that. So.
Brilliant. Great. Okay. Well, we'll get into all that and why you guys are so successful in the US at the moment and what you guys are up to. So just to kick things off, I think it would be really great if you could just give a bit of a background on yourself, because obviously, you've been at Exacta for more than 10 years on it, I believe now, and sort of worked your way from the build engineer role, I believe, all the way to CTO. So just give us a bit of a background on that. And then also after that, just a timeline of the Blackcore Technologies part of the group that you're focused on for our listeners, please.
Sure. So, I was told that I've been here for 13 years, which is a long time. And I'd say it's maybe a bit unusual in, particularly the tech industry. There's a lot of moving around and things like that. But I've been very fortunate that I've been able to grow with the company. So, like I said, I did start as a build engineer. I was, at 19, so very young, very green. But as a kid, I've always loved technology, as most people in tech did, and just did things like build my own gaming PC. Did a lot of let's say amateur coding and things like that. Building rubbish websites when I was 14 and those sorts of things. So always just loved the way tech works, and particularly hardware. I've just enjoyed kind of putting different things together and seeing what you can do with them. So I was lucky enough to get a job pretty quickly on here, and I was doing the build stuff. And I get very fuzzy on the dates, but within let's say within 6 months or so, I kind of moved from the build team to the kind of test and config role. So that was kind of, instead of putting things together, actually checking that things have been put together right. And what Exacta does, I imagine you kind of heard this from Nick last time, but we do a lot of installing of customer software and pre-config and staging and things like that. So it might be setting specific IPs before the device gets sent to the end client. So I was kind of getting involved in doing all of that stuff. And my experience with diagnosing my own hardware problems at home helped me kind of diagnose and fix any problems that we had in that testing process. And I did that role for quite a long time. And during that time, I started to pick up some of the support requests as well. So, a machine went faulty in the field. Typically the guys that have done all the testing are going to be the guys that have the best experience with, oh yeah, I've seen that before. If you do X, Y, Z, you can fix it. Or maybe you just know there's no recovering from that. We need to get that back or send out a replacement or something. So I started getting involved a lot on the support side. And that helped me get a kind of a good understanding of how clients typically use some of the hardware that we make, and maybe some of the things that they would expect, and how we maybe needed to shape our products going forward to meet those expectations. And during that time, which I believe is about 7 years ago, was when the first sort of beginnings of Blackcore started. At that time, we had a customer that asked us to develop an overclock system, not for the exact use case, but it was one of those things, could you do that? And some questions were asked around internally. I had experience with overclocking my home PC, and the kind of general consensus was, all right, we'll give it a go.
That gaming history is coming back for you there, mate.
Yeah. So. And we did this POC thing. I think it was like a 3 or 4U device with kind of like a standard gaming off-the-shelf liquid cooler and things like this. We did some minor overclocking, and the customer was pretty happy with it. That kind of led Nick down a path of, who is our CEO, is there some sort of market here where you can give clients extra performance than what they would typically get? And at the time, we had a contact at Intel called Mark Lawrence, who was a long kind of partner of ours on the tech side, and they've known Nick for a long time. And they started talking about this idea, and they decided to kind of run with that and try and build a product for that for the finance market. So at that time, I got kind of involved with helping out, kind of design the product and the overclocking and stuff like that. And to be honest, there was quite a lot of pain at the start. And obviously, building a new product is quite a challenge, particularly if you're going into a market you don't really know. So finance, we hadn't necessarily particularly been into, but also the overclocking niche within finance is also very challenging. It's very different to any other market. So there was a lot of lessons that we had to learn. And so there was some troubling times at the start. It was hard to know exactly what we were doing. And if you sell a standard service system into a market, you've got high confidence, as long as you're not doing anything stupid, that's going to work. And if there is any problem, the vendor, let's say you've sold a system from Supermicro, they're gonna, they've got the experience to say, this should work, this won't work, all these sorts of things. As soon as you start to do any tweaks to that hardware, i.e. overclocking, and we should probably kind of explain what overclocking is, which is you're taking a computer part and pushing it harder than it's meant to run. So the most common example is a CPU. If your CPU is designed to run at, say, 4 gigahertz, there are certain CPU SKUs that you can they come unlocked, is how they describe it, and that allows you to tweak settings to push them further. So you might be able to push that CPU to run at 4.5 gigahertz rather than 4 gigahertz. But what that means is you need to typically push more power into the CPU, and that's typically done by increasing the voltage you supply. That means it generates more heat, and you're also putting more stress on the actual internal components to supply that amount of power, and also to run with that amount of power and to perform those calculations faster. So you're taking something outside of its normal operating kind of procedure or kind of manufacturing specs, and all of that extra stuff, the heat, the power, puts strain on the system, and you have to account for that. You have to, cool it better. You have to provide, let's say you have to have a better motherboard or better components to provide power to the CPU in a clean way. You can't, if you've got like a bad motherboard, it might not be able to handle pushing that extra power into the CPU. And again, if you've got another aspect of this is not every CPU is the same. So even if you have let's say you've got 10 of the exact same CPU, they will not all behave the same. So they will all do the stock speeds. And Intel, so it's an Intel CPU. They've obviously done their R&D to describe, okay, we know that of all the CPUs we make 1,000 of these on a wafer, they will all hit these speeds. They've built that into their specification. As soon as you start to move outside of that specification, you start to uncover kind of the differences in the silicon quality of each CPU. So even though they're the exact same, they've got the same design underneath them, there might be tiny imperfections in how that CPU was made in the factory that start to become apparent as you overclock. We call that binning. So you're taking a range of CPUs, putting them through some tests, and you're binning them into different categories of, this one could push to 4.2, this one can push to 4.3. That's the general sort of background on overclocking. We can go on to that a bit more.
We'll touch.
But we kind of got sidetracked.
That's fine.
So yeah, we were obviously trying to do all of this stuff, and you're pushing these things harder, and so they start to become more unreliable because they're working outside of their standard operating procedures. Um, so designing a product around that is quite difficult, and that it took a long time to kind of get to the point where we are now, where we're very, very confident in our methodologies, the product design, and when you're dealing with clients that are very, very large, very big financial institutions, they've got obviously huge expectations, but they've also got a lot of kind of risk on their side. They can't risk having many machines fail or a high failure rate and things like that. So there's a lot of pressures on that kind of business model and the product development and all that sort of stuff.
Yeah.
So we went through a couple of iterations, and again, I was obviously involved with the kind of the overclocking side and some of the product design, but also I was involved a lot with the support side. So again, I was getting that feedback from some of our early clients. Typically we expect to be able to do X in the data center, or maybe there's a piece of management software that they're typically used to using with maybe a Dell or HP system. And a lot of that feedback helped shape where we went with the product development and the things we realized we needed to make, or change to our offerings. Eventually, just again, through natural growth, me being very ingrained in the design and the understanding of the product, and as Exacta grew, I helped build out the support teams, the R&D teams, product development teams, all these sorts of things. So I got very ingrained just in the very technical side of business and how the business needed to run and things like that. So eventually, here I am, kind of 13 years on in the CTO role, and yeah, really enjoying it. But it's probably it's quite a wide-ranging role when you're in we're obviously a smaller company, even with the growth we've had. So it's kind of many hats you have to wear. It would be a very different role compared to if you're a much larger CTO role in a different company. So we're kind of, in some ways, particularly on the Blackcore side, obviously Exacta, long-standing, we know what we're doing there. Creating these products for software vendors that we do, bespoke appliances. But that's our bread and butter. We do that every day. It's easy for us.
Yeah.
The Blackcore side, you can kind of see as more of a, even though it's been going for 7 years, it's more of a startup in some ways. It's a different business model to what we've traditionally dealt with, but also only in the last kind of couple of years have we really gone, okay, this is a serious business. There's serious growth that can be achieved here, and if we really put the time and effort into it, we can make something great.
Yeah.
So we're kind of in that stage of the startup phase of, okay, well, let's take this from a kind of an idea to a real thing.
Yeah, no, it's really interesting. I think Nick explained that really poignantly as well in the last podcast that we had. It's almost you've been in business for quite a large amount of time now, but you are very much in that start phase and that real growth phase. And he's got some very ambitious targets. So it sounds really exciting, and it's really interesting what you explain there about your role as CTO and very insightful. And it sounds far more hands-on than maybe some other CTO roles are right now, right?
Yeah, a lot of my kind of job these days is trying to remove that hands-on element. Building teams that can be self-sufficient, passing the knowledge on that I've learned over the last 13 years and saying, we need you to become self-sufficient, so that I can start taking a more high-level approach of, again, it comes back to those kind of features and client demands. Obviously I now do quite a lot of client-facing stuff, still on some of the support side, but also just kind of pre-sales, kind of product development stuff, and saying, what do you guys need? What's going to make you say, wow, this is great, or take our product from it's really fast, but it's lacking something. What's that stuff that we need? And then try and translate that and say, okay, for the next 6-12 months, we need to work on X feature. That's going to take us to the next level.
Yeah. Great. I think let's touch on that. Let's touch on the financial institutions and that industry that you guys are dealing with. And it couldn't sound like you could be in bed with more of a cutthroat industry if you tried. Very much demanding and a very interesting world. But I think what's important probably for our listeners to understand is why it's this way and why the kit that you provide is so important. And that probably comes down to higher frequency trading. So I think if you could just give her an explanation as to what that is firstly, and then we can get into it from there.
Yeah, so the stock market and the financial industry and all of that stuff is hugely complex. So, you could spend 10 podcasts and probably not, scratch the surface of some of it. And obviously we're also not, embedded directly in that industry and doing some of the things that our customers do day to day. So we're not experts, but we have a very good understanding of the hardware we provide and the task that our clients are trying to achieve. So what we would typically say is, we sell into the electronic trading industry. A part of that is the HFT industry. So electronic trading kind of encompasses all trading activity that's done via computers. HFT, or high frequency trading, kind of focuses on anything that's particularly latency sensitive. And without getting too into the weeds, there's various kind of levels to speed within the stock market, let's say. There's people that are doing things that are incredibly fast, down to a couple of hundred nanoseconds, and then there's things that move into more of a couple of microseconds, milliseconds, etc. So there's different kind of playing fields within the market, and different kind of firms that operate within each of those playing fields, or different strategies that apply to those different playing fields. Essentially, high frequency trading is, if I can react to a market event faster than anyone else, then I'm more likely to make a successful trade. Now, there's kind of two elements to that. There's having the right kind of strategy or algorithm. So you might hear about algorithmic trading, which is basically, algorithm is, if X happens, do Y. But if you have the best algorithm in the world, but someone beats you to that market event every time, then you're useless, right?
Yeah.
So there's a kind of mix of both that you need. And let's say if everyone was using the same hardware, they'd all have the same speeds. So there's essentially like an arms race that happens within the market. I need the fastest system to react quickest to the event. And again, this is split up into different playing fields within these kind of speed bands. So there's different kind of trading stacks that different firms are using to put themselves within these different bands. Obviously the systems we provide, overclocked systems, overclocked servers, are a kind of small piece of the trading stack. So typically what you might hear is something kind of software-based trading, and that would be something that runs in an application that runs on a standard system on the CPU, and you'll have network cards that bring in market data. There might be triggers that the software reacts to, then some sort of calculation, send that data back out with, I want to do X. And the faster you can react to that market data coming into your system, do some sort of calculation to say what you want to do, and then send your response back out, the better it is. If you were to compare a Blackcore system to a kind of stock system, and what we typically do is, for each of our products, we will compare our overclock to if you hadn't touched the system at all, which we call stock. Kind of typical stats we see is something like a 45% increase in clock speed. So that means taking, that 4 gigahertz up to 4.5 or whatever it is. But we also adjust various other factors within the system, like the memory, PCIe bus, things like this. So it's not just CPU speed, but it can be the cache on the CPU. So how quickly data can move around the CPU. It can be increasing the speed of the memory chips themselves. So how quickly you can get data from the CPU out to memory and back into the CPU. And that's based on larger data sets. A CPU can only hold a certain amount of data within itself and work on that data at a time. So sometimes you have to put data into RAM, whilst you work on a small part and pull bits in and out. Obviously there's a latency to do that. So the quicker you can get that data in and out of the CPU, the better, the faster you can turn your application around. And then the next part of that chain is actually moving that data. If I want to send a packet of data out to the network, I have to get that packet, construct it, send it to my network card, have the network card send that out to the wider network. So Blackcore's ecosystem is all about speeding up that entire chain.
Yeah.
And like I said, the clock speed side, we can see like 45% increase on memory and things like this. We can see decreases of up to like 35% in latency versus a stock system. So it's quite a significant amount, really.
Mm.
And the other aspect of our systems is if you've got a strategy based on certain market events, you want to be quite confident if I'm going to react to this market event, that I'm actually going to, my trade's going to get there and I'm going to, win that kind of trade. In order to do that, you need to understand how long it's actually going to take for that entire process to happen. And you need that understanding of how long that takes to be consistent. So if you had a system that, one day you run your algorithm and it takes, let's say, 100 milliseconds to do that activity, then the next time you go and do it, it takes 200 milliseconds, that can completely screw you over. Yeah. So you need kind of consistent and deterministic performance. And what a lot of people probably don't realize about if you've got a home PC or something, maybe you go and buy a CPU, you're building a PC, you see, I'm going to buy this CPU. It says it does, let's say, 5 gigahertz. And you're like, that's great, 5 gigahertz. That's the highest I can find. That's going to be really, really fast. Let's say it's also, maybe it's an 8-core CPU. So you go, I've got 8 cores at 5 gigahertz. What is kind of obscured from the user is that 5 gigahertz number that they advertise is actually only in certain conditions, i.e. if you're meeting power and thermal requirements, and typically it's only on 1 or 2 cores at a time. So if you've got a workload that's scaling across all 8 cores, the actual speed that you'll get is often much, much lower. It could be as low as 3.5 gigahertz or something. So you've just bought the CPU thinking, I'm going to get 5 gigahertz, but actually depending on what you're doing and the way modern CPUs work is there's a whole kind of power and voltage band kind of frequency curve that based on how much load is on the CPU, how much thermal load is on the CPU, and how much power is available, the CPU frequency is going to adjust itself. Yeah. And that's all about, the idea is your workloads are changing, particularly on a consumer PC. If I'm using Word, then I don't need to have my CPU running. It's like having your foot on the accelerator the constant time in your car. Yeah. It doesn't need to do that just to run Word. But what that means is when I do go to, let's say I'm using Word, I'm in a low power state. So that's what they call, or how they kind of define the bands, different power states. I'm using Word, I'm in a low power state. The CPU is just kind of ticking along. When I then go and, let's say I load up a game or I'm trying to run some sort of simulation for whatever reason, and that's a full whole CPU, hard workload, the CPU has to transition from that low power state into now the high power state. And you could kind of think of it as accelerating your car going, I'm in first gear, I need to get to 5th gear going 80 miles an hour. But that takes time. And depending on your car, it takes, longer or shorter, depending on how good the car is. That transitionary period could be the difference between, missing or losing that trade. Yeah. So what Blackcore does is go, okay, we're going to take this CPU. Let's say it's an 8-core CPU again. That's what the client needs. They need an 8-core CPU to divide their workload up across 8 cores. We take that CPU and we say, okay, what is the highest frequency we can push that to across all 8 cores and then lock it to that frequency. And the idea being you're going to get that frequency every single time. It's going to be consistent. The power states have been disabled or kind of removed. And you're getting a consistent, I know every time I run this piece of code, I'm going to get that performance out of the system. So it's kind of 2 elements. It's not just giving you more speed, it's giving you that speed at a consistent rate. Yeah,
gotcha. And I think what you've explained there really, really well, and where it pretty much all comes back to is, and probably people don't see it outside of what the traders are doing and the jobs that they're doing in their reactive state. But what you guys are doing are really giving a competitive edge to these institutions and the hedge funds with just, people don't see how important the infrastructure is to be able to go and do it, so that's probably really important for you guys, just that competitive edge that they can get.
Yeah, and like there's a lot of industries where that delay doesn't matter. It's a very short amount of time. But when your entire business is based on reaction, it suddenly makes a difference. If you're in the Olympics, having just had the Olympics, if you're a competitor in you have to react to the gun going off, and you've got a 10-millisecond delay compared to your competitor, you're going to lose, right? So it's very, very important in this specific use case. If you're doing something like, maybe you've got some AI simulation that takes 10 days to run, that 2-millisecond time of loading that workload, it doesn't really matter,
Yeah, no, that's great. And let's just go back to overclocking, and that's probably the important part here with these systems. And obviously, like anything, when there's benefits, there are fallbacks, there's pitfalls, and obviously with that, it's going to become stability and reliability. Just how are you guys managing it at this level with these guys?
So there's kind of two elements. A is experience. Like I said, we've now been doing this for 7 years in a kind of production enterprise environment level. And you just kind of build up a feel for the kind of underlying architecture of how the CPUs work, the kind of power bands and voltage bands that they operate in, and the temperatures that you can safely run at. So it's not something that is kind of easily learned. There's kind of trial and error, and that I talked about the kind of first year of the learnings or whatever we had to go through. And I would say that's almost key. It's almost necessary to teach you how these things actually behave, because it's very difficult. If you're talking something like your home PC, you can run an overclock on that. It might be stable in a couple of weeks. You play a random game and it happens to crash. It's not the end of the world. You might just go, oh, that's annoying, it crashed, but I'm just going to leave my overclock, and it might crash again in the future, but it doesn't really matter. But in an enterprise environment, obviously that failure is critical. It has a knock-on effect on your ability to do the work you're trying to do. So you have to figure out kind of how the CPUs are going to react over that period of time. And there's no easy kind of silver bullet way of saying for 100% that these frequencies with this voltage, that's going to last forever. So what we typically do is say our systems, we give a 2-year warranty. And there's obviously different warranty packages, etc. But the idea is based on our experience, we are comfortable saying that we can warrant these systems for that 2-year period, and we know the failure rate's going to be good. It's going to be low, and that's it's just purely experience. There's no other way I can really describe it. But the kind of other way we kind of operationalize around that is, systems will fail, particularly when you're pushing them outside of their kind of typical operating specifications. So it's how do you make any kind of failure that does happen have the least impact to the customer, right? So we have a couple of different warranty programs around. We can keep a spare system in the data center so that if the system fails, it's there, ready to go. All you have to do is swap over, a couple of connections or maybe the hard drives and stuff like that, and then that's up and running again. And then in the background, you can work on actually replacing the faulty system. So there's a couple of different programs like that we use just to kind of remove that burden of failure, or the burden of replacement and stuff like that from the business critical day-to-day trading. Outside of that, it's kind of how do we build the best system and get those failure rates down. The experience is one part. The second kind of aspect of that is having the best components or the right components to do what we're trying to do. So we're very selective on obviously the CPUs that we're using. Typically, they're split into different bands like consumer CPUs, kind of high-end workstation CPUs, and then enterprise-grade server CPUs. And we will typically use the best CPU in that range, and kind of build our product set around that. Two reasons for that is, A, typically it'll be the highest core count available for that range. And most of our clients are split into certain core counts that they're trying to fit their workload onto. And as you increase your core count, typically the kind of raw performance or raw latency increases. So the consumer CPUs have the highest performance and the lowest latency, but they're also the most limited on cores, memory size, cache, things like this. So they've got the best speed, but maybe not the best kind of feature sets or let's say bandwidth for everything you're trying to do. So you might be forced to then go into like the workstation environment. You might get a little bit less speed, but you might also get some, let's say again, if it's Intel, you might get some Intel technology on that or accelerator on that CPU that you don't get in the consumer market and things like this. So we choose the best parts of those. And then things like motherboard, we're very selective on having a motherboard that we know can provide the right amount of power to overclock on that system. But there's also things like, all of our clients being in enterprise markets, they need ways to remotely manage and access the systems. So we have to have a motherboard that has those kind of features. So IPMI remote management is key. And in most consumer boards, if you look at like, let's say, the highest rated consumer gaming motherboard, it's probably got way more kind of power delivery and power efficiency for overclocking than you could ever need, but it lacks any sort of enterprise feature level stuff. It's very niche consumer kind of overclocking focused. So we have to work with our partners to develop motherboards that have kind of the best of both worlds.
Yeah.
And this extends as well to memory and power supply and liquid cooling that I'll come on to in a minute. So memory, for example, we actually have a custom set of DDR5 SKUs that we supply of our systems. And historically, we used to go out to, again, typically the consumer market, and we would look at, vendors that were just offering off-the-shelf overclock memory. It might be something that's like 6,000 megahertz at kind of CL40 or something like that. Then we would take that, and that sounds great. 6,000 megahertz sounds like a really fast piece of RAM. But what most vendors are doing is, that frequency number is a good selling point. The higher the frequency, the better it is on the face of it. But the reality is, once you get into actually, particularly if you're latency focused, the frequency is not the main important thing. It's the memory timings behind that. So there's kind of a balancing act between more frequency and low timings. And there's a calculation you can do to kind of work out the kind of raw latency of the sticks based on those factors. So what we would do is take those DIMMs, and the higher the frequency DIMMs, typically they give you really great bandwidth, but they might be lacking a bit in latency. And we would tune those. Often we would reduce the frequency, but that would allow us to reduce the timings as well. And we'd end up with a kit that could read and write data, small amounts of data very quickly, and better than the stock DIMMs that we had bought. So we were doing all of that in-house, and when DDR5 came along, it was very different to DDR4, so there was a lot of new learning that had to be done, not just from the overclocking side, but just in the industry in general. The way those chips worked was quite different, and DDR4 was obviously a very mature technology at the time, so everyone knew exactly what they were doing, and most kits were quite similar.
Yeah.
So we took that as an opportunity to go, okay, we've just taken these new DIMMs, we've done a bunch of learning onto how they can overclock. Let's go to a vendor and say, can you make us a DIMM using some of the best memory chips on the market, and pre-pick and pre-bin for the kind of speeds that we want to do and the kind of memory times that we want to do. And we ended up coming up with a custom DDR5 DIMM. It's got our own little heat spreader on it for better thermal efficiency. And it's got a bit of bling to it. It's a nice little shiny thing that no one ever sees, but it's great for us. And so now we get those memory DIMMs in 9 times out of 10. Again, we were doing that binning process before. Now, 90-95% of those DIMMs come in and they work out of the box for our rated speeds. So that's increased, obviously, our production efficiency. But it also just means we know we're getting DIMMs that have been specifically made and tested to do the work that we're trying to do. And they're not just generic parts that we're kind of trying to shoehorn into our system.
Yeah.
So that was really great for us, and kind of a big step in kind of R&D projects that we have done. And we've also done things like our power supply. We just launched a new 2000 watt version. Power is constantly going up, and particularly on the higher end CPUs. I mean, most people in tech will have seen that CPU core counts are continually going up. Intel have in the workstation space like a 56 core on a single CPU right now. AMD have like 96 cores now on the Threadripper Pro stuff. So it's things that even 5 years ago were crazy, but in order to put that many cores on a CPU, the power draw goes up significantly. So some of our systems, if you really push them and load them up with as much kind of stress as you possibly can, they're pulling like 1.5 kilowatts from the socket on the wall, which is quite a lot of power. And a lot of that, if you take the 56 core CPU, for example, we overclock that, and it goes from being, from Intel, so I think a 300 watt TDP. Our system, the CPU, is around like 800 watts. So it's a significant amount of power, a significant increase. To deal with that, obviously you need a lot of cooling and better cooling, but you also need a lot of power to provide that. So we have a new 2000 watt power supply. We had that specifically designed for these higher power devices, but also, again, we used to use an off-the-shelf device. We've now had this customized so that kind of the way it provides the power is optimized, and then the kind of add-on connectors that we can plug into that power supply is customized as well. And it makes it a lot easier for us to design new products going forward, because we can add new cabling without having to change the power supply. Yeah. Cooling, we have our own custom cooling loop. It's very similar to a gaming loop, just kind of expanded to kind of an enterprise environment and to fit into a server chassis. So it's the same setup you expect. There's fans, radiator, there's a pump to move the fluid around, and then a water block or a cold plate that sits on top of the CPU. And we're constantly kind of evaluating the performance of that to try and improve our cooling. Obviously, there's two aspects to cooling. The more you can cool, the more you can push the chip, so it gives you more performance. But also, the cooler the CPU, or indeed the cooler the entire system runs, the more reliable it's going to be long term. So any component, the hotter it is and the longer it has to run in those hotter temperatures, the quicker it's going to degrade. So anything you can do to keep the entire system cooler is better. So we're always trying to evaluate that. And then the kind of final aspect, we actually make our own chassis. So we're not buying some 2U rack mount server chassis from a vendor in Taiwan or something like that. We actually design and build that in the UK. The great thing about that is it means we're very flexible and agile. We're able to tweak things and adjust things, almost on the fly. We've had clients come to us and say, "That's really good, but we put this card in and it's really, really hot card. So would you be able to put a fan in front of it?" And we're able to go away and go, "Yeah, give us a couple of weeks. We'll design a little bracket that we can add into the existing chassis, and turn that around really quick."
Yeah.
And that's something that you wouldn't be able to do that maybe with a tier one kind of enterprise system vendor.
Yeah,
so there's
yeah.
a lot of that kind of flexibility that our clients love about us as well.
Yeah, I mean, definitely. I think so. Just before we move into cooling, and just obviously liquid cooling and why there is such not a buzz, but we're hearing a lot more about it at the moment. But just especially a development and a component level, I wasn't really aware of the amount of customization that you guys had within your systems, and that's really interesting because obviously that can take time to customize to get what's right for you and your customers. But as you know, and specifically what we know from the memory market, these technologies move at such a speed. Before you know it, the latest PCIe or the latest DDR is moving, whether it be in mainstream or not. So are you guys constantly looking to test the latest and greatest components to see whether it works? And how are you managing the speed that things move? Is it a case of testing something and then, like you had done throughout your whole of the entirety, to see whether it works before moving it into a client? How does that work for you guys?
Yeah, I think it helps. Obviously, we're all the team here are all very technical focused, or had similar backgrounds to me. They love computers, they love technology, they love gaming. So a lot of us are very dialed into what's happening in the general industry. And we have like a Teams channel. We're often sharing. I've just seen this article on this new thing, and sharing our ideas about it. So one aspect is that you have to keep up to date, and the more eyes you can get on that, the better, and the more ideas you can share around, the better. And then I think as well, just from our experience, it's knowing what's relevant to our product and our industry, and then saying, okay, that looks really interesting. We need to try that. And then we've also obviously got very good relationships with our vendors. So, Intel and AMD are talking to us regularly, and we're getting roadmaps for what's coming and planning ahead. So we know, okay, maybe something's coming out next year. We need to get samples by this date, and we need to have a product ready by this date, and these sorts of things. So yeah, it's just keeping informed, doing the testing, and I guess there's kind of two kind of categories of advancement, let's say. One is pure performance. If we put this in, it's going to give us more performance. The other is around kind of either production efficiency. If we tweak how we make this chassis, we're going to be able to build it quicker. That makes it more efficient for us. And then there's the kind of user client-facing aspect. It's a case of like some of our early chassis designs, we had maybe some non-standard ways of adding PCIe cards in. The reason for that, without going into too much detail, is because of some of the cards that clients use don't easily fit into a standard 2U system. So we had to come up with some creative ways to make those fit. And some of the early implementations of that were quite clunky, and you had to take off like 10 different screws to get the bracket out and all this sort of stuff. So we have quite a lot of effort on moving our systems towards like a toolless design and all those sorts of things. Because at the end of the day, a lot of these systems are going into data centers, and then you've got remote hands in those data centers that are maybe adding or removing network cards and doing the racking and stacking. So the easier it is for them, the less they complain to the client, the less the client complains to us. So it's just, kind of performance focused and client focused, I would say.
Brilliant. Great. Okay. So let's move on to liquid cooling and why you guys use this in your servers. So firstly, I think, again, a lot of our listeners won't actually really have an understanding of what that is. So if you can just give a bit of an overview of what liquid cooling is and why it's so important, probably, I would imagine, from a heat dissipation standpoint, really, but just the full importance within your server specifically.
Yeah. So our servers use a kind of self-contained liquid cooling system. So the same way that, again, your gaming PC is self-contained, it sits within the chassis itself, and it doesn't require any external, water input or anything to make it work. We went down that route because we had kind of consistent performance. It was we had complete control over what was inside the system, and it's like a known quantity of the cooling capacity. On top of that, it can plug and play anywhere. You can put any Blackcore system in any rack, in any data center around the world. It's plug and play. All you need is power and network connections, etc. There are other technologies, other cooling technologies that require infrastructure within the data center, and so there's obviously a higher bar to entry there. And I think with our systems, we're pumping out a lot of heat, as we need to dissipate that heat. But it's on a scale that could be contained within a single system, whereas some of the other technologies are about cooling maybe removing less heat from a single system, but about tackling that lower amount of heat across an entire rack of systems at a time. So kind of two different approaches. If you're our system's giving a significant amount of heat from one very specific spot in the system. And with a kind of bespoke, self-contained system, you can directly target a high amount of heat. With other systems, you can target maybe a lower amount of heat, but the overall cooling capacity that system can take is much higher.
Yeah.
So, like I say, ours is self-contained. The other kind of two main types going on in the market, something called, there's different names for various things, but I always refer to this as kind of rack level liquid cooling. So let's say you've got an entire rack, and that rack is designed with a liquid cooling system built into it. And it will have piping that you put to each server system within the rack. And then your actual server systems going into that rack have to be designed, obviously, to take those pipes in, loop the liquid to the components, come back out. And that's a continual kind of circulation of liquid over every system within that rack. And that's in a kind of an efficiency and density gain. You can cool a large amount of systems with a very big kind of heat exchanger built into the rack. The issue there is you need, you've got the high cost of having the rack that can do that in the first place, and getting that rack into your data center, or your data center allowing you to have that rack in their space. And then you've got the aspect of now all the systems you buy have to be compatible with that system.
Yeah.
So it's kind of a higher, barrier to entry. But if you're doing something dense and all your systems are the same, maybe, then it starts to make efficiency sense.
Yeah.
But you also need infrastructure in a data center. Most of these racks typically are not self-contained. They require what they call facility water from the data center. So there has to be plumbing that the data center provides to give water to that rack, and it's cycled through. There's quite a high barrier to entry. There's going to data centers where they don't want to do that, or they're not ready to do that yet. And then the second kind of, or rather third kind of popular cooling technology we talked about at the minute is immersion cooling. So this is where you take, most people will call it like a bath. So you create like a bath, a big square box. So rather than having a rack that's normally very tall, it's now on the floor, quite wide, and you will put your systems down into it rather than horizontally into a rack. The unique thing about immersion is that bath is now filled with a mineral oil or a special liquid that provides the cooling capability, and that liquid is piped or pumped directly over all the systems in that bath. So and that sounds crazy, right? You're pushing liquid over over your surface systems.
Yeah.
It's not, there's nothing between the liquid and your systems. It runs through, directly over the components. Obviously, the liquid itself is a non-conductive liquid with a high kind of thermal efficiency. And again, it's kind of a density thing. It's easier to transfer heat into a liquid than it is to transfer heat into air. And you can kind of pump this mineral oil across all your components, absorb that heat, and dissipate that, either within the tank itself, if it's got a heat exchanger, or now a lot of the kind of, let's say, big hyperscale systems. The idea is you take that heat and you pipe it somewhere else to be heat exchanged. So there's some facilities, where they take all the heat, pipe it up to an air heat exchanger on the roof, and do the heat exchange there. And it's very, very efficient and great for density and power efficiency.
Yeah.
But again, obviously, there's a very high cost to that. There's infrastructure costs, facility costs. There's, a lot of data centers are based on kind of footprint and space. So often you will buy maybe a certain amount of space within a rack, or a certain number of racks or space within a data center. So you're kind of changing that dynamic now. You're not buying a rack, you're buying a bigger area of space to put your systems in and things like this. So it's a very complex dynamic, but if you're doing hyperscale stuff, it definitely can make sense from an efficient point of view. And there's also kind of, all these technologies make sense in isolation based on certain goals you're trying to achieve. And one of the other driving factors is just around kind of efficiency and the kind of power economy. So, there's a lot of focus on being green within the data center industry at the minute.
Yeah.
Obviously, power usage, I mentioned earlier, the CPUs are getting more and more power hungry, same with GPUs. You've gone from some of the NVIDIA GPUs, maybe with 300 watts, 200 watts. Now you've got AI accelerators that are 600 watts each, and you put 8 of those in a system, plus CPUs to drive them. You start to get an exponential growth in power usage. So there's a lot of focus. Again, if you've got an AI farm, that power it just exponentially grows. And if you can save 5%, 10% power usage, or reuse or gain efficiency back from that power usage, it can save a huge amount of cost on your data center bills. And then it also has the benefit of, if you can reuse that power, it's greener. We're all trying to make things greener. So how do they do that? How do they reuse that energy? Essentially, it's from recapturing the heat generated from using that power in the first place, and recycling it. So there's a lot of kind of movement and technology and work going on to essentially capture waste heat and figure out ways to reuse it. So there's a couple of projects and things many people are doing, like taking that waste heat and then using it to heat or power nearby facilities that could be homes. There's a couple of things in the UK where they're using that heat to power swimming pools and things like that. So it's just reusing that waste heat that otherwise would just be vented into the atmosphere. It's essentially lost money, lost efficiency, and figuring out ways that we can reuse that for kind of internal infrastructure.
Yeah, I think that the emphasis for data centers at the moment is really around sustainability. We know, sometimes they're seen as the bad guys, but at the end of the day, if we didn't have them, then we wouldn't have the internet, right? So it just wouldn't work. But, from what I've seen in the past, a lot of focus has been on PUE, and I've seen really cool traditional cooling systems, if you like. Probably at the time didn't think traditional, but adiabatic cooling and things like this. And it's not just all about efficiency, it's about sustainability now, isn't it? And like you said, really hitting on how people reuse the heat within their DCs.
Yeah, and I think obviously there's political and economical reasons and things like that. I think somewhat in the tech industry, a lot of people just don't like things that are inefficient. So you see it, even in the finance world, it's like, if I'm losing 10 nanoseconds here, that's annoying to me. I want to fix that. And it's the kind of the same with the sustainability element. It's like, people start to realize it's mental. I've got all this useful heat, essentially all this energy, and it's being wasted. I don't like that. How can I change that, and reuse it? So it's quite a good mix of, people in the industry and the problem to solve.
Yeah. So it's just, everyone's trying to be a winner in whatever they're doing, whether it's efficiency or sustainability, but, sustainability is very much an important thing. So that's really, really helpful and really, really great to hear from you on that. So I think just to wrap up, I would like to just touch on just looking into the future a bit, and largely around obviously the evolution of AI and HPC and where we are right now. What predictions do you see ahead for the fintech industry in this area?
Yeah, I think you kind of have to split it into two different categories again. There's, at least for the electronic trading stuff, you've kind of got the hyper dense compute stuff where you're maybe trying to do real-time analytics, or you're doing historical analysis of market data, and you're doing a lot of number crunching, and that's going to be super dense stuff. It might be AI, it might just be general compute, but with bigger core counts and things like that. That's obviously, as we said, ever increasing in power. So there's always a kind of battle between performance gains versus cost and sustainability and all those sorts of things. And then there's the second kind of category, which is the low latency trading aspect of, I want the fastest thing. So obviously you kind of see there's two different markets as well, with Intel and AMD and NVIDIA, what they're targeting. There's that dense market of cramming as many cores as we can into a system, or as many compute units into a single server. to increase that density. And then there's the other aspect of making the actual individual cores themselves as fast as possible or more efficient at doing certain calculations. So on the very low latency side, that trend will continue. CPUs are going to get faster. They're going to get clever in how they do the calculations that they do. And some of that as well is around increasing the amount of cache or system memory that's available to the CPU directly within itself. So reducing other bottlenecks that makes the CPU faster. So it's not waiting on data to come in and things like that, rather than just making it faster at doing each calculation. And then on the density side, just as that grows, they will continue looking at that. I kind of got a funny story. You often ask, I guess internally within the finance kind of firms, you've got people that manage the hardware, you've got kind of the business level stuff of, cost and efficiency and all those sorts of things. And then you've got the kind of trading teams that, they just want the fastest thing or the best thing for them. And they, whatever's going to make their algorithms work the best. And, often you'll get, they're kind of vying for each other. I want the best thing. Okay, well, I want the most cost-effective thing. Okay, well, I want the hardware that's easiest to manage, sort of thing. And so sometimes you'll get asked, "Oh, yeah, that's really great, but could you do it, at a lower power rating? Well, can you make it more efficient?" And you go, "Yeah, I can do that, but you're going to lose 10% performance." "Oh no, we can't do that." So it's like, there's this battle constantly going on. We want more power efficiency, but we don't want to lose performance. So the systems, sort of CPUs and the technology coming out that can give you more performance at lower power usage and power efficiency, I think that'll definitely be key to the financial industry, but the entire technology market as a whole.
Yeah, brilliant. Yeah, well, that moves fast, so things will move fast for you on that end, I want to imagine. So, no, brilliant. Look, James, thank you for coming on today and sharing everything with us. It was very, very, very enjoyable chat with you. And we really look forward to following your journey here at Sims, and we will do our best to bring that out into the open as well. So, thank you, and I hope to speak to you soon.
No worries. Thank you very much.
Cheers.